Hi, it's great to be here in Portland. And thanks for stopping by on this sunny afternoon for a talk on computational physics. So the doors are still open in case somebody came here by mistake. There still is some time. Now, how many people know who Feynman is? Okay, almost everybody. There are a few who don't, so for them, I'll just introduce them who this guy is. So everybody knows who Newton is, but I think it's slightly interesting to see who Feynman is. So he's a guy who is a legend among the physics community. But it's not only just his physics was extraordinary, but he was quite a character. So if you don't know who he is, you should probably check out Feynman. You can search for his videos on gravitational physics and so on, but he was quite a bongo player also. And his great lectures on physics, which he taught in Caltech in 1961, is a classic of physics. And a few years ago, Caltech put it all online. So anybody now can go and check out those lectures and see his teaching. So let's now go to the main part of the talk, which is about using Python for calculating planetary orbits. And so I'm Pramod Gupta. I'm a research scientist at the Department of Astronomy of the University of Washington. And the thing we'll focus on today is Kepler's first law. The planets move around the sun in an elliptical orbit with the sun at one of the two foci of the ellipse. So Kepler found this after many years of extraordinarily hard work and brilliant thinking from Tycho Brahe's data. And you need to keep in mind that the data was taken with respect to the Earth. And Kepler had to think about how it is with respect to the sun, which was an extraordinary problem. And just as a reminder, this is what an ellipse looks like. It's sort of like a squished circle, but it has a very precise definition. The distance, the sum of the distance from the two foci is a constant. And so Newton applied his laws of motion and the law of gravity to the orbit of the planets and derived Kepler's laws. And this, again, was another extraordinary piece of work. But the derivation requires advanced mathematics. So even hundreds of years later, it's not an easy problem. And it's generally taught to physics students towards maybe their third or fourth year of their study. And the question is that, is there some other way? This is Feynman's blackboard from when he was teaching his lectures. And it's interesting what he points out in the last line. Feynman was not, he made a lot of great discoveries, but this particular thing which he's saying there is not his discovery. It was well known before. But usually you learned about it if you went on to do advanced physics. You did not learn about this in your freshman physics class, where you did mostly much more simpler problems. So this is what he's saying. So for those of you who have forgotten cursive handwriting, he's saying if the force law is known as a function of position and velocities, then the equations, so he's referring to Newton's equations, can be solved in close approximation, step by step in time, by arithmetic, okay? So he's saying we can do this all by arithmetic. And all of us here know arithmetic from our grade school and elementary school. And so how should we go about this calculating of the orbit? And Feynman tells us this work can be done rather easily by using a table of squares, cubes, reciprocals, and then we need only multiply x by 1 by r cubed, which we do on a slide rule. So how many people here brought their slide rules with them? Oh, there are a few still. Okay. So for those of you who don't know what a slide rule looks like, so this is the thing. So the secret is get a slide rule. But we have computers. So the computer can do arithmetic. And if you have a few $100 million, this is the computer you want to buy. But the amazing thing is that computers have become so much faster over the past 50 years since Feynman gave his lectures that even the regular off-the-shelf laptop can do those computations pretty quickly. But we must tell it what to compute. So the fun and games part of the talk is over. And we come to Newton's law of gravity. And essentially what Newton is telling us is that the force between two objects, in this case a planet and the sun, is proportional to the product of their masses. The big M is the sun, the little m is the planet, and r is the distance of the planet from the sun. So that tells us the magnitude, the numerical value of the force. But it's a vector, which means that we need to think about the direction. So the direction of the force is from the planet to the sun, which this arrow over here shows. And we need to take two components. So from your high school geometry class, you can see that this big triangle over here, this triangle, and this little triangle over here, the force triangle and the position triangle, are similar triangles. And you can use that to actually show that the x component of the force is the magnitude of the force, and then you multiply it by x divided by r. And similarly for the y component of the force. Now Newton, not only he had his law of gravity, he also has his second law, F is equal to ma, which along with E is equal to mc square is probably the most famous equation in physics. You see it on T-shirts and places like that. And you need to equate these two forces. And what happens is that the little m drops out, which actually is sort of an amazing coincidence. And it took over 200 years later for Einstein to actually explain why that happens. But in any case, you get an expression for the acceleration, the x component, and the y component of the acceleration. So we've done some algebra here, which is fairly straightforward. The question is, how do we use this information to compute the orbit? So we'll do a few more algebraic manipulations just for convenience. And I'm closely following chapter 9 of Feynman's lectures. So I would highly recommend you go and check it out. Because it's an incredible, very readable way of writing. He just tells you just the right amount of details which are required to solve this problem. So we just choose units such that big G and big M are 1. This is just for convenience in calculations, but the computer doesn't care. You could use the actual big G and big M values. And we have the acceleration over here, the x component. It becomes slightly simpler looking, and the y component. And one more thing we need to remember is Pythagoras' theorem. So the distance from the sun to the planet is given by the square root of x squared plus y squared. And these are just a few definitions, really, that the position is given by x and y. The velocity of the planet is given by v sub x and v sub y, and the acceleration is given by a sub x and a sub y. So we just saw that we already know the acceleration from Newton's two laws. In this slide, all you need to keep into account is this. So if you remember your calculus, the other stuff will make sense to you. But all you need to remember is the 1, 2, 3, 4, the fourth line. So if you know the position of the particle, or the planet in this case, at time t, and you know the velocity, you can calculate the position at a time t plus epsilon, where epsilon is the traditional mathematical notation, a Greek symbol for a very small value. And similarly, you can find the velocity at a time t plus epsilon, which is, again, the fourth line over there. It's not showing up in the highlighting there. And what this tells you is that if you know the position and the velocity at some given time, you can use this arithmetic procedure to keep calculating it for the next slightly later time, and then the slightly later time, and so on. And that's what we'll do. Now, Feynman uses Leapfrog integration, which is more accurate And it also has some nice properties. It conserves energy so that if you go around the whole orbit, you don't lose energy. You don't spiral into the sun. And it also has time reversal symmetry, which means that if you start from a given position and do this calculation, and then you change the sign of epsilon, you make it minus epsilon, and you start going back, you'll come back to the same position that you started. So a lot of other techniques don't have that property. Now, Feynman doesn't mention it because he's a great teacher, but I just couldn't resist putting these two lines here. And what this means is that if you do leapfrog integration, you do the same thing we did earlier, but we calculate the velocity at a time offset by epsilon by 2. What that means is that you do the position calculations at integer values of epsilon, and you do the velocity calculations at half integer values, so epsilon by 2, 3 epsilon by 2, and so on. And so you can see why they call it leapfrog. Essentially, you go the position values leapfrog over the velocity values, and the velocity values leapfrog over the position values, okay? And this gives you much more accuracy for those of you who remember your calculus classes, is because you're considering the velocity at the middle of the time interval and not at either end. And so we know the initial position and velocity, and using that we can calculate the acceleration over here, and we can also calculate the velocity at epsilon by 2, okay? So we need this offset value of the velocity, as I just mentioned, because we are going to do this leapfrog integration, just like Feynman did it. And so this is the first iteration. It might look a bit complicated, but it's fairly simple. You can think of it kind of like in a recursive sort of way. So the position at a time epsilon is equal to the position at the time 0 plus epsilon times the velocity at time epsilon by 2. Okay, so it's, if you know, it's like a lot of things in programming. If you know x for I, then you can know x for I plus 1 using some assignment statement. And this is just given here for completeness, which is the general case. But I'm not going to talk about it, since it's much easier, actually, to just look at this formula and do it manually using a calculator or a computer, as we can easily do now. And I'll choose the initial conditions which Feynman used. Basically, what he used was some conditions which are very convenient for the calculation, which is essentially saying that you start the planet at x value of 0.5 and a 0 value for y. So it's right on the x axis. And you give it some velocity in the y direction. So it's at the x-axis, and you give it some value in the y direction for its velocity. And one more thing we need to do is choose the step size epsilon. So Feynman, note that epsilon is nowhere in the physics. Okay, Newton didn't know anything about epsilon, and Feynman used epsilon equal to 0.1 to minimize computation. So, but the smaller the epsilon value that you use, the better accuracy that you get. And since computers are so incredibly fast nowadays, we'll use epsilon is equal to 0.001 for the same initial conditions that he used. For other initial conditions, one may need an even smaller epsilon. And this is one of the things about computational physics, that you have all these epsilons and mesh size and things like that, and you need to make sure that they are small enough for the problem that you're looking at. And this is Feynman's solution. And it's very interesting. So they did it manually back in the day with slide rules and things like that. And to save slide rule time, not computer time, to save the slide rule time, he just did it for a half orbit. So he didn't do it all the way. So it's not necessarily obvious from this that this is a closed orbit. But you can see a lot of interesting features here, that when you're close to the sun, it travels longer distances here. And when it's far away from the sun, the planet travels much shorter distances here. And that's related to Kepler's second law, which I'll not talk about. But you can also get Kepler's third law doing these kind of calculations. And now what I would like to do is talk a bit about the code. Since all of you use Python on a daily basis, you might be wondering, all this is fine, but how complicated is it to put it actually in real Python code, functioning code, not just hand-waving arguments? And so all we need to do is set up epsilon and the number of steps you want to take in your loop. So that's just one simple thing we need to do. We use the initial conditions. So we set up, all of you do a lot of programming, so you know that initialization is very critical. And you need to initialize things properly. And we'll use the same conditions that Feynman used. But this is just so that we can match up our calculation with his calculations. But you can always play around. That's the fun part of all this, that you can write your own code and then play around with these initial conditions. We allocate some memory for the lists we'll use. We initialize the starting values. And again, this is just putting into Python code the stuff which I wrote earlier in mathematical form. And you can see that it's very straightforward. You initialize your position, you initialize your acceleration, and you initialize your velocity. Note that the velocity is offset by epsilon by 2. So the 0 index for velocity means that you're already epsilon by 2 progressed in time. And this is the main loop. So this is really the only main critical part where we are using, we are calculating x of I when we already know x of I minus 1 and v sub x of I minus 1. So essentially, as Feynman is saying, all we need is arithmetic. All that the computer is doing here is some straightforward arithmetic. And it's doing it many times. We are doing it 10,000 times. Feynman in his calculation did it maybe 20 or so, some much smaller number of times as you saw on that plot. And at the end, we can plot the orbit with these matplotlib commands. And one of the motivations for this talk is the fact that, well, one of them was the lectures are now available online for anybody to look at. And the other motivation is that it's, over the last few years, you have these nice packages, nicely built distributions for Python, like Anaconda and Canopy and so on. So you can install them anywhere, and you'll automatically get all these things, like matplotlib and so on. And you don't need to be a big expert in installing stuff. With that, I would like to first run some of the code. So this is going to be a bit, it's always interesting doing a live running of code. I'll just show you the code for a second so that you can see it's essentially the same code that I showed you in the slides, but I just want to show it also in the actual code. So this is code we'll do a live run of. So there's no extra fancy stuff. And let's run it for Newton's, for Feynman's initial conditions. And you saw it took less than a second, something which would have taken a long time. And you can see it's a nice ellipse shape. And that tells you actually that Newton's laws, his law of gravity and his law of motion, actually contain these things. As Feynman used to like to say that Schrödinger equation, that's the equation for quantum mechanics, contains frogs, but we can't solve it in enough complexity to actually show that it contains frogs. But here we can show that Newton's equations contain Kepler's laws. And we have a nice ellipse shape here. And one thing I like about matplotlib is that you can do these zooming things. So if you click here, you can zoom into this rectangle. And you can see that this 0, 0 position is where the sun is. That's one of the foci. And there's another foci somewhere here. And you get a nice elliptical shape. But this is not all you can do with all this. You can actually say what happens. So this is much easier this way with computational approach than with necessarily with the more advanced mathematical approach. What you could do is you could say, what happens if I increase the velocity? And you can see the planet escapes orbit. So you can actually see that if your planet has too much energy, or if whatever is orbiting the sun has too much energy, it's going to escape. And what happens if you decrease the velocity, which means you decreasing the energy also? OK, that looks weird. Now let's see what that means. If you zoom in, you find that it's not a closed orbit. So what's happening is that the orbit seems to be shifting, and it never comes back to the same point. But we have not discovered any kind of new effect here. The problem is that our epsilon is too big for this particular case. So we need to decrease epsilon. And now we get this nice ellipse shape. And note that it's very elliptical, so to speak. This is the position of the sun over here. So when it's close to the sun, this planet, so it's unlikely a planet would have orbit like this. But things like comets and so on have very elliptical orbits where they go off way out very far away, and then they come back, they're very close to the, relatively close to the sun. So this is the kind of orbit which may not be so common for a planet, but it could happen to other kind of objects. So let's go back to the presentation. So we saw the code. And I'd like to conclude with Feynman's own words here, where he says that now armed with the tremendous power of Newton's laws, we can not only calculate such simple motions. So he was talking about particle on a spring and so on. But he's saying we can not only calculate such simple motions, but also given only a machine to handle the arithmetic. And nowadays, all of us have such a machine to handle the arithmetic. Even the tremendously complex motions of the planets to as high a degree of precision as we wish. So essentially, and in his chapter 9, he shows how you could do the same thing for the whole solar system, which in his days was like 9 planets. Now we only regard it as 8 planets. But basically, you can put in all the planets, calculate all the forces, do this computation step by step, and make a model of the solar system, a realistic model on your computer. And so with that, I would like to conclude. And I hope some of you at least go and look up Feynman's chapter 9. I would like to conclude this talk and open it up for questions.
So we are open for questions.
Hi, that was really interesting. Thank you for the talk. One question I had is you showed the ellipse that sort of degrades because your epsilon wasn't small enough to simulate it correctly. Do you have any thoughts, or are there any standard ways of telling if you get an unusual result from a numerical simulation that's not what you expected? Are there ways of knowing whether that's a fault with your simulation code or if it's a fault with your parameters? Like, how do you tell the difference between an unexpected effect that actually really is there and an unexpected effect that's caused by how you happen to be doing a simulation?
Right, so that's an important question. And generally in computational physics, often you don't, so here we knew the answer. But generally you may not know the answer. And the way to tackle that essentially is to vary these parameters like epsilon, which are not really there in the physics. So if you see something funny, you try something finer, say. So you decrease your epsilon. And unless you notice a pattern where no matter how small your epsilon is, you keep seeing the same thing, then you think that maybe this is a real effect. But generally, that's the way you go about solving a problem which you don't know the answer to.
Thank you.
Hi. So this might be a long answer, but you mentioned that the Leapfrog method preserves energy. And suppose, so if you don't use the leapfrog method, do you not preserve energy even if you use like a lower accuracy? And if so, why does the leapfrog method work so well at preserving energy?
So the thing about the leapfrog method is that it has this time reversal symmetry, so up to machine precision, okay? So, and that is what causes it to have this extra property of preserving the energy. So if you calculated the energy, which is half mv square plus the potential energy due to gravity, it would not trend to a lower or possibly even a higher way. It would stay steady. Maybe a little bit oscillations, but it would not create a situation where your planet sort of goes into the sun. And so essentially, compared to a lot of other techniques, this particular thing has, the leapfrog method has this property because of the time reversal symmetry. So.
All right, thanks.
Yeah.
Any other questions? So let's thank Pramod.